So let's talk about phase, and our goal with talking about phase is to come with just a little wider way of thinking about simple harmonic motion. The equations that you've learned so far are completely valid with respect to time, but they only really deal with one example, and that is the example in which we start the simple harmonic oscillator at its maximum amplitude. But obviously, any simple harmonic oscillator does not necessarily have to start at its maximum displacement or at the amplitude. It could actually be started anywhere, and so we need to have a little more general way of thinking about the simple harmonic oscillator that can handle all situations instead of very common. It's very common for simple harmonic oscillators to start in this manner, but they just don't have to. So it kind of narrows down our ability to describe the motion of the simple harmonic oscillator with respect to time to just a very narrow class of oscillators, although they are common. So the phase refers to the fraction of the wave cycle that has elapsed relative to the origin. And you can actually see an example of how phase is evident if we look at, for example, the displacement versus the velocity time graph. So if you'll notice that they look identical in that they have a negative and a positive maximum, a negative and a positive maximum, but they are in a sense offset from each other. So the way we would describe that is that the displacement time graph, if you notice, its maximum negative occurs here, whereas for velocity it occurs back here. So what we would say is that the two graphs are out of phase with each other by a quarter of a cycle. A quarter of a cycle would be pi over 2, or we could say 90 degrees. They're 90 degrees out of phase with each other. So at every position where the velocity is, the displacement is pi over 2 ahead of that position. Or we can think of it in the other manner, that the velocity reaches that position, that maximum negative, for example, pi over 2 before this guy does. So where this occurred at pi over 2 and this position occurred at pi, we can see for every corresponding position reaching the equilibrium or reaching the zero position, but on the ascending, same thing over here. It's pi over 2 later than it occurred for the velocity time graph. So this is an example of two graphs that are out of phase with each other. They follow the same cycle, but they've been shifted by some small amount that represents the phase. So just to give you an example, we've looked at this equation that x is equal to a cosine omega t. And that works great as long as the oscillator at time equals 0 is at its maximum amplitude, because the only place where, when we start at t equals 0, the only way for this cosine to become positive 1 is if the argument would be 0, or any multiple of 2 pi. So when t is equal to 0, that guarantees that what's in the parentheses is 0, that guarantees that the cosine is at its maximum value of positive 1, and therefore that's a situation in which the oscillator is started at t equals 0 at its amplitude, or at its maximum displacement. But it's not hard to imagine a situation where it wouldn't necessarily start like that. So let me give you an example that would not be described very adequately by that equation. So let's say that we have a pendulum, and the pendulum has already been pulled out. So I might be, for example, holding the pendulum right here. And what I'm going to do is, rather than release the pendulum and allow it to start to swing back, instead what we're going to do is we're going to take a small hammer and we're going to strike the pendulum bob and send that pendulum bob upward even further. Now, if we allow time equals 0 to be the point where the hammer hits the ball and the ball begins to move, then that situation is not very well described by this, because it's not at its maximum amplitude at t equals 0. So this cosine is going to give me 1 because the argument in here is 0. And that's great if it's at its maximum amplitude, but the maximum amplitude in this case is going to be much greater, because this is going to go up even further. And it wouldn't matter if I, for example, hit it in the opposite direction. It would still not be at its maximum amplitude, because by striking it and giving it velocity at time equals 0, remember in our old equation at t equals 0 there was no velocity. There was no velocity at t equals 0. So no matter which way I hit this thing, it's not at its maximum amplitude, and at time equals 0 it is not at 0 velocity. So this equation is not going to suffice to be able to describe this one. So let's look at a little more generalized simple harmonic motion versus time. Alright, so what's missing is somehow we have to account for the fact that the maximum amplitude actually occurs at some later time. And the way that we would do that is, the equation looks essentially the same, except that we need to add something to address the fact that it's not, that relative to the traditional origin, which would be at its maximum amplitude, it's not quite there. So we add something that in most books would be referred to as phi. So the displacement is a cosine omega t plus phi, or phi. Now let me show you graphically how that looks. Let's use this one as an example. And so this is x and negative x. So here's where we started. Okay, we have some displacement, but the problem is that the maximum displacement occurs at some point later. And so the way this graph is going to look is it already has velocity. Remember that the previous graph, before we draw this, remember that the previous graph, the slope was 0 because it had no velocity at the beginning. But in this case, this guy is going to start with some velocity, so there is some positive slope. Then we reach the point at which there is no velocity, and that's where it reaches up here to its maximum, where the pendulum bob comes up here to this new point and reaches, now it really will be at 0 velocity, so we'd expect to see the slope of this line flatten out, and then we'll see it start to go in the opposite direction. Okay, and here's the point at which we would have completed one full cycle. That is to say, we would be in the exact same position where we started. But the problem is that at time equals 0, we are not at a position of its maximum displacement. So that phi factor is going to basically, right, here's the place where I've reached A, the maximum amplitude, right? But it didn't occur at t equals 0. So that phi factor is right there. Okay, so by adding phi, that's going to allow us to have this at some displacement which is not quite at its maximum, but at some point it could even be negative in terms of its value. This whole thing could be shifted. Essentially what we've done is, if you look at the original graph that we drew, right, this entire graph, imagine that it's been shifted over by some small factor, that factor being referred to as the phase factor. Now this is really truly the generalized equation. This will address any possibility, regardless of where that simple harmonic oscillator starts. That equation is going to be able to describe it. Now, for our purposes, we're really not going to be too concerned about the phase factor. So instead, what we're going to do is we're basically going to look at two extreme positions. So we're going to make a note of this. So I'm going to split the paper in half, and we'll take a look at how the equations work out. And what we're basically going to do is we're going to find a way in which we don't really have to worry about this phase, because in the two extreme situations, what we can do is use the trig functions sine and cosine, which are naturally out of phase with each other by pi over 2, or 90 degrees, or a quarter of a cycle. They're naturally out of phase with each other. I mean, the sine and the cosine graphs look exactly the same, except for the fact that they start at a different location in their cycle. One starts at its maximum, one starts at 0. They're always off by 90 degrees from each other. So let's look at the two possibilities, and in order to do that, we'll split the paper in two. Okay, so possibility 1 is start at A. That is to say, to start at the maximum displacement, the amplitude, with V equal to 0. Now that's exactly the situation that we've already looked at that situation. That's this situation. Remember, for the pendulum, the displacement only refers to the horizontal displacement. It's not actually following the arc. We're only concerned about the horizontal displacement. So in this case, the equation x equals a cosine omega t is perfectly valid. Essentially, what we're talking about here is phi is equal to 0. We don't need to worry about phi because phi is equal to 0, and therefore the velocity is going to be minus a omega sine of omega t. Again, the phase factor of the phase is 0. In terms of the acceleration, I'm not going to write the acceleration because, again, remember that a is equal to minus omega, the acceleration that is equal to minus omega squared x, and then here's x, so you can always recreate that acceleration equation. But I do want to point out is that in the data booklet, they don't use the letter a to represent the amplitude. They use a slightly different variation of it. So if you remember, I told you that x naught could also be a way of describing that, and then v would be equal to this is the way that it's going to look in the data booklet. In this particular example, when x is at its maximum, this is at time equals 0, at t equals 0, v will be at a value of 0, but as soon as time starts moving, as soon as we start moving through the cycle, the velocity is immediately going to be negative because we're on the positive side, but at the maximum, when it's released, the velocity is negative, and that accounts for why we have this negative sign in front of the equation. Okay? Now, the other possibility would be this extreme situation, and that is that we start at equilibrium. So when I say the other extreme possibility, I don't mean the other amplitude on the other side, because effectively that's exactly the same. These equations will describe the other side over here at the negative amplitude just as well as it would on the positive side. The other extreme is to start this thing at equilibrium, and one thing that you can be absolutely guaranteed is that no matter how you start this thing, regardless of the starting position of this, you will always reach your maximum velocity when you reach equilibrium. Even in this situation, going back here, so I strike the thing, I give it some velocity, it will slow down, reaching 0 velocity up here, and then it will start to come back down, but it will be at its fastest when it reaches the equilibrium position, which for the pendulum is when the pendulum bob is directly beneath the support point. So what I'd like to do with this one is we're going to take that hammer and we're going to strike the pendulum bob, and that is going to send this guy moving up along his curved path. And so at t equals 0, I'm actually going to be giving it its maximum velocity. This is the point where it's at the bottom. It will have no displacement, that is to say it will be at the equilibrium position. It will swing up a quarter of a cycle later, it will reach its maximum displacement, called the amplitude. It will then have reached 0 velocity, it will come back down, reaching the maximum velocity, overshoot. That's halfway through the cycle. 3/4 of the way through the cycle, we're over here at the negative, and then finally we'll return back here, and at that point we just keep repeating that cycle. Now, here's what we could do. We could use a phase factor of 90 degrees, or pi over 2, to account for the fact, and then we could use the same equation. But since the sine and cosine are naturally out of phase with each other by pi over 2, or 90 degrees, what we could do is we could simply flip the functions. So we could say x is equal to a sine omega t. And then how would that look? Well, at t equals 0, the sine of 0 is 0, so x is 0. That's exactly our case. a quarter of the cycle through, or pi over 2 through the cycle, when omega t is equal to pi over 2, then the sine will be positive 1. That will be the maximum amplitude. That's exactly the situation that we're looking at here. And it will continue through the cycle appropriately based on the sine function instead of the cosine function. So if you notice that the two look almost identical, except we just swapped out sine for cosine. The velocity, now this is tricky. This is really tricky. If you notice that the velocity will be positive as the displacement starts out in the positive direction. So x is positive any place over here, and x is negative any place over here. But the velocity is a little tricky. So the velocity is positive on this side, and then it starts moving back. So now it's moving in the negative direction. Now it's moving in the negative direction. Now it's moving in the positive direction. So you can't say that the velocity is positive or negative depending on which side of the equilibrium position it's on. It could be either positive or negative. And just to show you that, you can see that back on the graph. Look, positive displacement, but negative velocity. That's in the first quarter of the cycle. In the second quarter of the cycle, negative displacement and negative velocity. In the next quarter of the cycle, negative displacement, but positive velocity. And in the last section, we have positive displacement and we have positive velocity. So this velocity thing it's a little tricky in the situation where we're flipping the trig functions to a different version of from cosine to sine. In this case, there would be no negative. So we would have a omega cosine omega t. When we strike this thing, it will be moving with its maximum velocity, and it will be moving in the positive direction. So there is no negative sign in front of this. That's really, for you to think about, to decide whether there should be a positive or negative in front of that velocity equation. You just have to sit and think about the direction that it's moving relative to which side that it's starting on. Just as I showed you, there is an alternate way of writing. Instead of using a in the data booklet, they're going to use x naught. So this would be simply x naught sine omega t, and then for v, that would be x naught omega cosine omega t. And as we pointed out, the cosine at t equals 0, the argument in here will be 0 no matter what omega is. Cosine of 0 is 1, and we'll get our maximum velocity, which is a times omega. Or the same thing down here, the amplitude x naught times omega. Cosine will be 1 at t equals 0. We'll be at our maximum velocity, and that's exactly the situation that we described. So these are the two extreme situations where we can use simple trig functions without having to deal with this phase factor. But I did want you to see the phase factor, because if you go a little deeper into physics, or you take a class that's a little longer, spends a little more time on this, you'll definitely need to become familiar with this phase factor and how to handle that. But for our purposes, we'll just deal with the two extreme situations, and we can solve them. You can solve them with phi. You can use that, but you don't really need to, because the two trig functions are 90 degrees out of phase with each other.